All right. Well, welcome everybody to the Robert Ferguson Observatory Speaker Series. My name is Stephanie Dromalar. I'm the Executive Director of the Observatory, and we're so thrilled to have Elinor Gates here from the Lick Observatory with us, and I'm going to introduce her in a second. But before we start, just wanted to remind everybody to please keep yourselves muted. We are going to do questions at the end, so if you can as you think of them, even if it's during her talk, go ahead and put questions in the chat, and then I will facilitate those for her at the end. So first, a little bit about, obviously I see a bunch of familiar faces and names here, but for those of you who are not familiar with the Robert Ferguson Observatory, sorry, letting more people in here. So the Robert Ferguson Observatory is run by the Valley of the Moon Observatory Association, which is a 501(c) nonprofit comprised of volunteer, amateur, and professional astronomers. And RFO has fulfilled its mission of offering educational programs about science and astronomy for students, the public, and in support of educators for about 25 years now. The observatory is almost all volunteer run, and it typically serves about 9,000 visitors annually. I'm happy to say that this year is looking almost close to a typical year. The observatory is located in beautiful Sugarloaf Ridge State Park in in Kenwood, Sonoma County, and houses a 40-inch reflector telescope, which is the largest telescope in Northern California. That's accessible to the public, I should say, a robotic 20-inch research grade or CCD telescope, and an 8-inch 2-meter-long refractor telescope. Like I mentioned, the observatory has a robust volunteer program with close to 200 volunteers who really work tirelessly to deliver all our programs and manage public star parties and solar viewing events, provide classes, etc., and manage a ton of behind the scenes tasks as well to keep the observatory running smoothly. If anyone is interested in volunteering, it's a great way to get involved. And there's a volunteer application on our website, rfo.org. Membership is another great way to get involved and support the observatory. And the membership application is also on rfo.org. And as a member, you can attend any of our public star parties for free and get good discounts on our other classes and events. Lastly, I wanted to mention we've kept the presentations in our speaker series free to the public to align with our mission of offering educational-based astronomy programs to the community. That being said, if anyone is so inspired to donate to the Robert Ferguson Observatory to ensure that we can fulfill, or I should say continue fulfilling our mission, that would be, of course, greatly appreciated. And you can also do that through our website, rfo.org. So now for the good part, to introduce Dr. Elinor Gates. She is a staff astronomer at Lick Observatory, specializing in laser guide star adaptive optics and near-infrared camera instrumentation and observations. She did her undergraduate studies majoring in mathematics and astrophysics at Mount Holyoke College. She received her Ph.D. in physics and astronomy from the University of New Mexico in 1998. Before moving to Lick Observatory, she worked at the Smithsonian Astrophysical Observatory, IAU Minor Planet Center, the National Radio Astronomy Observatory, and the Air Force Phillips Laboratory. Dr. Gates's current research interests are studying quasars and their host galaxies, discovering dust-obscured quasars, and measuring the masses of quasar and AGN central black holes. And a fun, which I think is like a very fun fact, is that asteroid 2650 Elinor is named in Dr. Gates's honor, which I think is super cool to have an asteroid named after yourself. So without further ado, Dr. Gates, I'm going to pass it on to you.
Okay, great, thank you. Let me get my screen shared here. Come on, play. There we go. Okay, so I'm going to talk a little bit about the science and technology innovations that we do at Lick Observatory. I'm going to focus more on hardware and instrumentation because that is my main focus of research and what I've been working on most recently. But just for those of you that don't know about Lick Observatory, It sits on top of Mount Hamilton, east of San Jose, on the highest peak in the San Francisco Bay Area. So it's just over 4,200 feet. And it was the first permanently occupied and year-round accessible mountaintop observatory in the world, of course, setting the trend for all future major research observatories. The observatory was founded by James Lick, who gave $700,000 of his over $3 million fortune to build the greatest telescope in the world. Unfortunately, James Lick did not live to see the construction of the 36-inch refractor, but it is his tombstone. He wanted to be buried at the base of the telescope, so it's there as his monument, and was ready to be used in 1888. And the first discovery made with this telescope was on January 7th in 1888. The second day the telescope was used. The first day was January 3rd, 1888, and the weather closed in, and they discovered the telescope didn't focus properly. So they did a few days of work, and on January 7th, 1888, James Keeler looked at Saturn, and he discovered a new gap in the rings of Saturn, and he named it the Encke Gap. Later on, when Voyager went by Saturn and discovered yet another gap in the A ring of Saturn, they named it the Keeler Gap in his honor. Another early discovery at Lick Observatory, using the great telescope that James Lick funded, was the discovery of Amalthea, the fifth moon of Jupiter. And before that, only the 4 moons discovered by Galileo were known. And it was the last moon in our solar system to be discovered using visual techniques. That is not, just looking through an eyepiece and very careful observations by Edward Emerson Barnard, who is most famous probably for Barnard's star, a high proper motion star in the sky. And all moons in our solar system discovered since then have been using photographic techniques. So anyway, early history of the observatory, it was turned over to the University of California after it was completed in 1888. And it is one of the primary research facilities for astronomers in the University of California, as well as educating the students of California at all levels. So we're going to zoom forward in time to 2020 and talking about what has happened in the past few years. Of course, it's been a couple turbulent years between the pandemic, wildfires. So I'm going to talk a little bit about that. But I want to first talk about the major research telescopes we have here at Mount Hamilton, and what sort of research they were doing before the pandemic began. And so our largest telescope is the Shane 3-meter reflector. So it has a 3-meter diameter primary mirror, and it is our primary research instrument. And it has a number of different cameras and instruments that we can put on the telescope. The CAS spectrograph is the most frequently used one. This is an instrument that takes the light from a star or galaxy and spreads out the light into all its component colors. So spectrographs work much like a prism, taking sunlight and making a rainbow. And spectrograph just spreads out the light so you can see what colors are in abundance or missing in the spectrum, and you can use that information to measure how fast something is moving towards or away from you, what it's made of, its temperature. All sorts of interesting information come from a spectrograph. And the CAS spectrograph, as I said, is our most frequently used instrument on the Shane telescope. We also have the Hamilton spectrometer, which is a very high resolution spectrograph. So it's sort of like the CAS spectrograph, but on steroids. It spreads out the light much further, so you can see many more details. And that spectrometer is mostly used for discovering planets around other stars. And of the first 100 planets discovered around other stars, about 70 of them were discovered here at Lick Observatory using that Hamilton spectrometer. And then we have an infrared camera that works with our adaptive optics system. So I'm going to spend a little bit of time talking about adaptive optics. One, because it's my specialty and the instrument I work with most. And two, because we're going to talk a lot about new innovations in adaptive optics that we're doing here at Lick Observatory. Adaptive optics is a technique that sharpens your images through the telescope. So the Earth's atmosphere is turbulent and blurs your images through a telescope. So that even a large 3-meter telescope might not see details any better than maybe a 10 or 12-inch telescope in your backyard because of the atmospheric turbulence. With adaptive optics, we can actually measure the turbulence and correct for it in real time, sharpening our images, so that with the 3-meter telescope, we can get images sharper than the Hubble Space Telescope when things are working well. And I have this nice animation that came from the Gemini North adaptive optics system, but it gives you an intuitive feel for sort of what adaptive optics is doing to give us the best possible images through our telescope. So here in the animation, you're going to see that the light is coming through the telescope, bouncing off the primary mirror, off the secondary mirror, then going through a hole in the primary mirror to the instrument on the back of the telescope. And so we're going to get a little cutaway view of a very simple adaptive optics system. You can see the light bouncing off the mirrors. And we have, let's see, do I have a cursor here? Somewhere here. Yeah. So you can see that in the image, it's all bouncing around and jiggling because of atmospheric turbulence. And so that turbulence is deformed potato chips flying through the system. That's how the light is bent as the turbulence in the atmosphere does it. So we call that a wavefront. And then we tell the computer system to use the wavefront sensor and then use a computer to calculate what the turbulence is and put opposite turbulence on the mirror that can change its shape, in our case, over 1,500 times a second, to put anti-turbulence on the mirror to clean it up. So you get rid of the turbulence and all of a sudden you get these nice, beautiful point-like images through your telescope. Now, this is great because that means you can do what's called high contrast, high resolution imaging. So that you can, otherwise the star is a big blob in long exposures. But when you have adaptive optics, you shrink that core down to the theoretical minimum size that your telescope can see, the highest resolution, and you can see faint objects around it that would otherwise be obscured. This technique is remarkably effective, but what you need is a bright star so that you can measure the turbulence. Now, a bright star is something like 12th magnitude or brighter. So our eyes see stars down to about 6th magnitude, and 12th magnitude is maybe something 600 or so times fainter than what your eye can see. So that's not terribly bright, but still in our terminology, it's a bright star. And if you don't have a bright natural star to make these turbulence measurements, you can actually use a laser and create a fake star wherever you need one to make these same measurements. And so Lick Observatory pioneered this technique called laser guide star adaptive optics. So you can see in this picture, we have a little small telescope, a 12-inch diameter telescope on the side of our 3-meter telescope, where the laser comes out of the telescope. And then that goes up to this 60 miles up above our heads and causes sodium atoms in our atmosphere that are deposited by meteors burning up at about 60 miles up. And those sodium atoms that used to be in meteors fluoresce when they get hit by this specific color yellow laser. And so we can create a fake star wherever we need one, so that we can use this technique even if we don't have a bright star. Now, bright stars work better than the laser because the laser is only sampling 60 miles of our atmosphere, where star is going through all of the atmosphere. But it is remarkably effective. And of course, we pioneered this technology at Lick Observatory, and it is now used at virtually all large telescopes around the world. Here's a sample image of what it looks like through our 3-meter telescope. So this is Uranus, a planet in our own solar system. And hopefully you can see in this image that Uranus has storms on it. So you can see the details of the storms, as well as I hope you can see the faint ring. Uranus has a ring around it, much like Saturn. It's just not as impressive a ring. And you can also see some of the moons of Uranus in this image as well. So we actually have a regular program here at Lick Observatory that I work on, monitoring the atmospheres of Uranus and Neptune. So every clear night, when we're during Uranus and Neptune observing season that we're using the AO system, we try to get data on its storms to monitor them, see how they change in time, see if we can figure out how, deep in the atmosphere or not they are based on the different color information we look at in the near infrared. So it's a long-term program we're working on. And we also do the same thing with the Keck telescope in Hawaii. Those are 10-meter diameter telescopes so that we can monitor the storms on Uranus and Neptune. And I collaborate with Imke de Pater and her graduate students at University of California, Berkeley on that. Now, Uranus is bright enough that we don't need the laser guide star, but then you have objects like this planetary nebula, IC 2003. On the left, you can see the planetary nebula without adaptive optics. It just looks like a star, an undifferentiated blob, but with adaptive optics, and it's faint enough, we need to use the laser. You can see the white dwarf at its core and the nebulosity around it that's expanding. So for those of you that maybe don't know what a planetary nebula is, it is essentially a star like our sun that has died. And before it died, it turned into a red giant. They're sort of unstable and they sort of puff off their outer layers and the core collapses to a white dwarf in their death throes. And so our own sun in some 5 billion years or so will probably look very much like this planetary nebula. So this is just a couple examples of the sorts of science we're doing with our 3-meter telescope and the technologies we're using. Our second largest telescope on Mount Hamilton is the automated planet finder. So with the 3-meter telescope and its Hamilton spectrograph, it was so successful discovering planets around other stars that the researchers, Steve Vogt, Deborah Fisher, and other people from UC Berkeley and a number of other organizations around the world were able to get enough money to buy a dedicated 2.4-meter diameter telescope that's robotic, that's sole purpose is to find planets around other stars. And so it's using what's called the radial velocity technique. And so with the radial velocity technique, when you have a planet orbiting a star, as in this graphic, they both orbit around the common center of mass. So this animation is hugely exaggerated in how much wobble a small planet causes on its parent star. But you can actually use a spectrograph to measure the tiny motions back and forth towards and away from us on a star caused by a planet. So we're not seeing the planet directly, it's far too faint, but we're seeing its effect on its parent star. And whoops, next slide. And so how we see this in the spectrum is we spread the light out, and they're usually dark bands of absorption caused by hydrogen atoms and other atoms and molecules in the atmosphere, the photosphere of the star. And you can see those stars when those dark lines are, when the star is moving towards us, those lines move to the blue. And when the star's moving away from us, I have difficulty getting the words out. The dark lines will move to the red. And so you see this oscillation back and forth. Now, the automated planet finder, because it's specially designed to be a robotic telescope to find these planets, it can detect a speed with an accuracy to about 1 meter per second. So most of us can easily walk. 1 meter per second is actually a slow stroll. It's not even walking fast. And to think that we can, for hundreds or thousands of light years away, measure the wobble of a star back and forth to that sort of accuracy and infer the presence of a planet. As I said, we don't see it directly, but we infer the presence of a planet. And so this telescope, robotic, does this work every single clear night of the year when we can open the dome. They would have loved to have done that with our 3-meter telescope and the Hamilton spectrograph, but they have to share that 3-meter telescope with all the other astronomers in the UC system. And so they couldn't get enough nights. And so having a dedicated telescope for their program has allowed them to discover many stars. or many planets around other stars. And in fact, they've discovered many solar systems around other stars. So here's an example that Steve Vogt published back in 2015 of a planetary system that has 6 planets orbiting it. Now, most of these planets, the easy planets to detect with this technique, tend to be the really big planets really close to the parent star, these super Jupiters and things. But the goal of the automated planet finder is to discover more rocky planets like Earth around the sun. You know, and many have been discovered at this point. So it's pretty exciting, and that just does its thing every night. Our next largest research telescope is the nickel reflector. This is a 1-meter diameter telescope. And until recently had only 2 instruments we were using on it. We were using a direct imaging camera, just taking pictures of the sky and various filters. You can see an example of one image I took with it of the Trifid Nebula on the right-hand side, telescope itself. So direct imaging camera, most of the science done with the nickel telescope tends to be looking at supernova explosions and following them up, tracking their brightness over years. We have a large program of undergraduate students that get trained on this telescope to how to do this program and do these observations on a regular basis. And then we have an instrument called NIROSETI, and that's the one that's shown mounted at the bottom of the nickel telescope. NIROSETI stands for Near Infrared and Optical Search for Extraterrestrial Intelligence. And NIROSETI is using what are called photomultipliers. They're essentially photon detectors. So they're detecting light and 3 channels, so that any signal that might be coming from a laser beam from another civilization out there in space, it would have to be detected in all 3 channels to make sure that it's a real signal, because other things can look like a short laser pulse that aren't. Things like cosmic rays, radioactive decay events, things like that. But those things are random and will only trigger 1 channel. So if it triggers all 3 channels, there's a chance it's a real signal. And then, of course, it has to repeat so that you know that it's a real laser signal and maybe there's really extraterrestrial life out there. So this is a long-term program run by Dr. Shelley Wright at UC San Diego. She actually started as an undergraduate student at UC Santa Cruz. So she's worked on this for many, many years with Frank Drake and Dan Wertheimer and a number of other people at the SETI Institute. And then we have new instruments coming this year and into next year, a wavefront sensor and LAMAS. So I'll talk about those later. So those are little teasers for what's coming up later in the talk for our newest, latest, and greatest programs. Another thing that the nickel telescope is used for is detecting kilonova events. Kilonovas are when you have 2 neutron stars spiraling into each other and they merge, they collide and merge. At observatories like LIGO can discover. And so we have a program run by Ryan Foley at UC Santa Cruz, where he is looking for the gravitational wave detectors detecting a possible kilonova. And because it's 2 neutron stars merging, not 2 black holes, there's an optical explosion, an afterglow that they can detect from these events. So when LIGO discovers a possible kilonova event, they will submit what's called a target of opportunity request to the nickel telescope. And the nickel telescope will interrupt its operations to look at the right part of the sky to try and see this afterglow of 2 neutron stars colliding. So they started this program, and then the pandemic happened, and they had to stop. And then they started doing upgrades on LIGO. So it's been out of service for a while, but soon they will be starting this back up again now that they have the gravitational wave detectors coming back online after the pandemic and upgrades. So with luck, we'll get some really cool observations of these neutron star merger events as well. Our next research telescope is another robotic telescope here at Lick Observatory called the Katzmann Automated Imaging Telescope, or CATE for short. And this is a telescope that's been in operation since the 1990s as a robotic telescope. So it's one of the very early robotic telescopes in the world. And its sole purpose is to look at galaxies, hoping to find a supernova explosion. So we can look at up to 1,000 galaxies a night, take a quick picture of it, a quick snapshot, and compare it to the image it took maybe the night before, a few nights before, the last time the weather was good. And it looks for a new star appearing in that galaxy. And if it sees something, it says, aha, I might have something, I need to look at it again. And so its program will automatically do another observation in a few hours or the next night to confirm and make sure that new star that's appeared in the galaxy is still there and a real event. Because it can be confused, because there are things like asteroids that might move through the field, or nowadays many, many more satellites than there used to be. Or it could be a cosmic ray or other random event that you might see in one image and not the next. All these data get reviewed by undergraduate students at UC Berkeley. This program is actually run by Alex Filipenko. And these students, comb over the data, because while the computer and the robot are good, they're not as good as human beings at finding all the supernovae. So here are a couple sample images. On the left, we have supernova 1994D. This was a type 1A supernova. So type 1A supernovae are when you have a white dwarf star with a companion red giant star. And the white dwarf star is stealing mass from the red giant star, and it's accreting onto the white dwarf. And when the white dwarf hits 1.4 times the mass of our sun, it explodes and in a supernova explosion. And so it's this enormously bright new star in the galaxy. In fact, sometimes the supernova explosion might be brighter than the whole rest of the galaxy. But it'll get bright over a series of weeks to months and then fade away. The other type of supernova is a type 2 supernova, and on the right hand side you can see a type 2 supernova 1998S time series showing the initial explosion of the type 2 supernova, which is when a star many, many, many times more massive than our sun at the end of its life, instead of dying in a very sedate planetary nebula fashion, like the planetary nebula I showed earlier in the talk, they blow themselves to bits in a supernova. And so these are, giant stars exploding at the end of their lives. Both are interesting. And of course, there are lots of subtypes and lots of details. But the CATE telescope, when it first came into robotic operation in the 90s, was discovering on average 2 supernova a week. When the whole rest of the world at that time was discovering maybe 24, and that included all professionals, all amateurs, all over the world. So it quickly became the world leader in supernova discoveries. Now, there are many, many telescopes that do this sort of research. So we've changed our goal. Our goal is to look at fewer galaxies, but detect that supernova much sooner after it explodes, so that we're looking at each galaxy much more frequently in hopes of finding that supernova explosion mere hours after it explodes, as opposed to maybe days or weeks as it used to be. So anyway, this is a summary of sort of the major research programs and the major telescopes that were going on in 2019 and early 2020. And of course, then, as all of us know, COVID happened and everything came to a screeching halt. We started having meetings among the leadership teams, so Zoom became super important, as we all know. And I'm not going to dwell on this because we've all lived through the pandemic and we've probably had enough of it. But we did have to shut down completely all our operations. We weren't allowed to go into the domes, only our skeleton crew going in to maintain instruments and the facility to make sure that, rain wasn't getting in, things were remaining heated, cameras were staying cold. So everything stopped except our robotic telescopes. Our robotic telescopes, because they didn't need people, just kept turning on. But if something broke, it would take long time to get permission to go in there and do the necessary repairs. But I was very excited. In the lower left-hand picture here are my colleagues, David Black and Chris Latliff, installing a new wavefront sensor in our adaptive optics system, new improved system. And that went in February, and then in March, we were all ready to test it, and then we couldn't. So that got quite delayed. And of course, all our other instrument upgrades and science just came to a screeching halt. Of course, we also have active public programs. And so in early April, it became obvious we wouldn't be able to do any of our in-person public programs, our telescope viewings, our concert series, everything got canceled. And we started working on how to make our telescopes remotely operable. Most of our telescopes required people to be on site operating a telescope. So we needed to do a boot camp to quickly update software and do what we could to make it possible to use some of our telescopes remotely. We designed what we call the pajama observing mode, so that you could observe from home in your pajamas if you wanted to. And that started with the nickel telescope on April 14th. So it didn't take us too long to rehash all the software. Unfortunately, the other telescopes, major telescopes that weren't robotic, couldn't operate because they really required a human being at the telescope, and we weren't allowed to go into the domes because of COVID safety measures. Eventually, COVID restrictions, we learned more about it and we're able to get that. So we were able to return our 3-meter telescope to operation in June of 2020. But we couldn't reopen to the public to do our public programs until August of 2021. And that was not just because of the pandemic and COVID, but also because we had the SCU wildfire, which I'll talk a little bit about. That caused enough damage at the observatory to shut us down for quite a while. Anyway, one of the instruments that kept running through the pandemic, which was brand new at the observatory, once we figured out how to remotely open the dome and do some necessary things, was PANOSETI. So I already mentioned NIROSETI, looking for laser signals from other civilizations. PANOSETI is the next generation. So this stands for Pulsed All-Sky Near Infrared Optical SETI. And so you can see in the picture here, we have the dome open and 2 telescopes looking out. Now, each telescope has a field of view of 10 degrees. So the moon, for comparison, is half a degree across. So this is 20 times the size of the full moon across in a field. So it's looking at a huge field. These telescopes don't steer. Right now, they're just pointed looking up towards the south. And we're allowing the sky to drift over them, looking for these laser signals. And it's using a new technology called multi-pixel photon counters. And these are great because they're sensitive to light all the way from the near UV, bluer than our eyes can see, about 300 nanometer wavelength, all the way into the near infrared at 1650 nanometer wavelength. So this is a huge range of colors of light they can detect. And they're looking for all these transient pulsed laser signals. Now, we use laser communication here on Earth, so, maybe intelligent extraterrestrial civilization would be using laser signals. But what's exciting to me about this program is not just that we might discover other light, but we're examining a whole new parameter space. There are lots of things out there that pulse at different speeds or have different time frames for their events. So you have pulsars, which are neutron stars that emit light sort of like a lighthouse and spin very quickly, that can pulse anywhere from a few times a second to 1,000 times a second. So they're spinning very fast. So you can in the plot. And then you have things that happen much more slowly, like novae and supernovae. Gamma ray burst afterglows can have timescales of minutes to days or seconds to minutes. But PANOSETI is looking at these things, these nanosecond length pulses. We've never had an instrument before that could detect light signals that short. And so we may discover not just laser signals from other civilizations, but new astrophysical phenomena that take on the time scale of, nanoseconds to a second. And so we don't know what we're going to discover. So we'll just have to see what happens. But this instrument was installed in 2019. It was just getting started when we had to stop everything because of the pandemic. But once we managed things and got back up and running, it's now running most clear nights looking for things. And this is a test program. If this all works, we'll have much better telescopes that can point, look at the whole sky. But this is just a proof of concept test program using these new technologies. So as I mentioned, the nickel telescope, we made the pajama observing software. And when we got back to observing on April 14th, they were looking at supernova explosions. So these are supernovae that were discovered by the Kate telescope or other robotic telescopes around the world. And in the image here, this is what the observer sees. Use our direct imaging camera, and the first object observed would be the supernova 2020 HLA. So I hope you can see it. My cursor, there's a little faint galaxy next to it. So it's in that galaxy, and you have the bright supernova, brighter than the whole rest of the galaxy combined. And so the students were monitoring that. So science was happening with the nickel telescope when we were moving forward after the pandemic. The Shane telescope took a lot longer to get running after the pandemic shutdowns. Mostly because we weren't allowed to go into the domes until the university figured out the proper safety mechanisms and all the shelter in place, et cetera, that people here in the Bay Area experienced. I mean, really all around the world had similar experience. But anyway, we came to a compromise that we couldn't have two staff members in the building at the same time for safety. And so the instrument that was on the telescope was CAS spectrograph. So that was the science that could be done. Fortunately, the CAS spectrograph is our most frequently used instrument on the Shane telescope. So again, when the first science happened, it happened to be a supernova they were imaging, or actually taking a spectrum of. So this happened to be a type 2 supernova, whereas the other one observed on the nickel telescope was a type 1. But this type 2 supernova, they were taking a spectrum. And actually, this one is a polarized supernova. So there are two channels here looking at the polarized light from the supernova. So if you look at the image here, the vertical bright line in the image on the left is the supernova. And then you see these bright horizontal lines are either lights from San Jose, like the sodium lamps in San Jose, or mercury lamps, or bright lines in our atmosphere that just happen to emit a lot of light as well. But the supernova is there. And in this picture, the bluer wavelengths are up at the top of the image and the redder wavelengths are at the bottom. But again, they use this spectrum to not only look at identify what kind of supernova it was, but what its polarization was. So as I said, we were doing science again. Everything was great. And in fact, there's another telescope I haven't mentioned yet called the Coudet Auxiliary Telescope that uses that Hamilton spectrograph. So when the Hamilton spectrograph isn't being used on the 3 meter, we have a smaller 24-inch telescope that can feed it. And in July of 2020, the Parker Solar Probe was flying by Venus. And one of my colleagues, John Reese, was part of our program to look for aurora on the dark side of Venus caused by the sun, high energy particles from the sun. And so he was taking spectra of Venus, looking for aurora on Venus in conjunction with the Parker Solar Probe, looking for the same thing as it flew by Venus. So it was pretty interesting work, but it was only possible because John Reese, like me, is a staff astronomer here at Lick Observatory and lives on site. And so there was no travel involved, and he could go in and work by himself in the dome on this telescope and not worry about other people with COVID being around. So, as I said, getting lots of new innovative science done. We thought, this is great. We've managed the pandemic. And then unfortunately, August occurred. And on August 16th, there was massive lightning storms. And so this is a time lapse from one of our web cameras. And you can see there's a fire here caused by lightning at the right-hand side. You can see a little red glow and smoke. That fire is the one that grew and overtook Lick Observatory in just a couple days. So, we've had lightning spark fires before in the area, not really caused Lick Observatory troubles. This one, unfortunately, grew and moved south towards the observatory. Eventually, the first buildings affected were the two houses that you see here in the lower left of the movie, showing the lightning storm. And in fact, one of those houses still isn't habitable. It's still too damaged from the fire, so we haven't fully recovered from the fire. But on the night, about 11 p.m. on August 18th, the observatory got the evacuation order because there's only one road to Lick Observatory. The road to the east of us was already blocked by the Canyon wildfire and the Calaveras fire as it moved towards us. Eventually, all of these fires merged to become the Santa Clara Lightning Complex Fire. But we all evacuated. Essentially, we had just enough time to, grab our, pets, family, a few necessities and leave. The morning of August 19th, CAL FIRE and the Office of Emergency Services had an enormous number of fire trucks at Lick Observatory. They not only were here to protect the observatory, but the surrounding ranches and areas, and they were using Lick Observatory as a command post, being the highest point in the Bay Area. Our historic main building that's shown in these pictures was also a safe zone for them. But about 3 o'clock in the afternoon, 3:15 is when the fire first hit Lick Observatory. So the flames in the upper left picture on the order of 150 to 200 feet high. So this was an enormous firestorm that came and hit the observatory, hit the residential region we call Tortilla Flats first, then moved further south, hitting Rattlesnake Ridge. And this house that's completely in flames was the historic home of Edward Emerson Barnard back in the 1890s, completely destroyed by the fire. So we had a few buildings destroyed by the fire. All the telescopes survived, but 8 or 9 of the residences had damage. Some of them so bad they couldn't be lived in, and are still awaiting repairs. But the firefighters did an amazing job of saving as much as they could, considering how violent the fire front was. It's truly astonishing that we survived, but we 3 buildings were completely destroyed. 8 houses were damaged, but all the telescopes made it. But we had no power, so we were running on generator for a month. All our staff were evacuated for about a month. A few key people were allowed to return to the site with working with the sheriff and firefighters to come up and help restore our power and internet and water infrastructure and stuff that was damaged. We had our generator running, which gave power for essential communications. You can see in the upper left picture here lots of communication towers. So our generator was helping communications for the fire departments. And everything else. So it's quite dramatic. But after about a month, the staff started returning and started cleaning up. And cleanup required. There was soot and ash in all the telescope domes, so everything needed to be cleaned from the top down. A lot of our optics we cleaned with a commercial product called First Contact, which is sort of a liquid you smear on. And then when it dries, you can peel it off. And with luck, it takes all the junk off the mirror and leaves it clean. We also had to wash all the domes. So there's my colleague, Adam Nichols, on top of the 3-meter telescope dome, essentially making it rain, gently washing all the soot and ash off the dome so we could open it without raining fresh ash onto all our freshly cleaned telescopes. It took us quite a while But by the end of October, so this was about 2 months after the fire, all of our telescopes, all of our research telescopes were back in operation. So, we're still recovering. We still haven't replaced all the damaged buildings, fixed all the houses, but at least the telescopes are running. And we got back to operations, at least in the pandemic sort of normal. But we started implementing new telescopes, because we're not ones to stay idle. We're going to test out new things. And the first new telescope at Mount Hamilton after the fire was PEAS. PEAS stands for Planet as Exoplanet Analog Spectrograph. So PEAS is a 1/2 meter plane wave brand telescope, and it's on wheels, so it lives in the basement of a 120-inch or 3-meter Shane telescope, and undergraduates will roll it out, align it, and take data on bright planets in our own solar system. So why are we looking at planets in our own solar system with a 1/2 meter telescope? Well, we're trying to figure out how to take images or data from exoplanets, planets around other stars, which we can't resolve them. We can't see all the details. But planets in our solar system, we can see all the details of. So we take some of the light from a planet like Jupiter and send it to an imaging camera. And then we take the rest of the light and send it off to what's called an integrating sphere. And this is essentially a gizmo that scrambles the light so that you get all the light, but it's all scrambled. You don't see the individual details, the spatial details. And then they send it to a spectrograph to see what comes out and what they can see. Because when we are just now having the technology, particularly with the James Webb Space Telescope, to look at the atmospheres of planets around other stars, that the star, when a planet moves in front of its parent star, it absorbs some of the light from its parent star. And because if that planet has an atmosphere, different colors of light are going to be absorbed differently by the planet's atmosphere. And so you get the spectral information about what's in the atmosphere, but you don't get a whole lot of information about storms. When you look at a planet like Jupiter, it has storms, it has a non-uniform surface. So we're trying to work backwards to say, okay, if we scramble the light and make it look more like an exoplanet's light would look like from an instrument like the James Webb Space Telescope, or similar instrument, infer what can we figure out based on this sort of scrambled, non-resolved light, based on what we know of instruments, planets in our own solar system. I hope I'm making sense. I don't feel like I'm explaining this very well, but it's a very cool concept, because it's what we can get from data from our own solar system with this instrument will help us interpret data from the bigger telescopes like James Webb Space Telescope. Anyway, this had first light in November of 2020. It was a very cold, windy night, but they looked at Mars. And so you can see all the spectra of Mars here, and then a comparison for the sky. So yes, they were really looking at Mars. And of course, I have to go and analyze all this data, figure out that out. But this is a program run by Emily Martin and Andy Schemer at UC Santa Cruz. And they're the ones in the photo, all bundle up there for our cold November night. So that's just one of our new programs. Another new program is called PANOSETI, or as I say, it's PANOSETI Plus. So I already talked about PANOSETI with those 2 telescopes that just stare straight up to have a big field of view looking for laser pulses. What they discovered with PANOSETI is because it's so sensitive to short time duration events, it's really good at seeing things like flashes of light from high energy particles hitting the Earth's atmosphere. And those are nearby, and they realize, aha, if we have 2 telescopes separated by about 1/2 mile and connected by a fiber optic, because there's parallax, things that are happening in our own atmosphere from high energy particles hitting the Earth's atmosphere, you can discern those from things that are out in space that are farther away, like these laser pulses or other astrophysical physical phenomena they hope to discover with PANOSETI. So back in June of 2022, Jerome Mayer here is assembling the new telescope and installing it in this tiny little dome. That's where the Barnard House used to be. So the one good thing to come out of fire is it cleared out an old building that wasn't being used very well and gave us a fresh building site to put a new telescope. I think it's the only maybe good thing that came out of the fire. But it's very slick because they now can discern this. And this is, again, a test program. They're now looking at building a new pair of, or two new arrays of telescopes, one at this Barnard House site and the other one further east. So they have a longer separation between the two telescopes that will even allow them to better discriminate between these atmospheric events and astrophysical events with their telescopes. So that's moving forward, trying to get funding to build new telescopes. They still haven't discovered any laser signals that they can confirm yet from other civilizations. So the search for extraterrestrial intelligence is still pending. Now I'm going to focus a little bit more on adaptive optics specialty stuff, and I'm going to go over this very quickly. Partly because it's all so new and we're still testing everything, so we have no final results yet. But I mentioned with adaptive optics very early in the talk about these things called wavefronts and wavefront sensors that measure the turbulence in the Earth's atmosphere. Now, the Nickel telescope does not have an adaptive optics system, but Micah Van Kooten at UC Santa Cruz has installed a wavefront sensor in our guide camera path. So the light from the 40-inch telescope comes down through this hole, hits this mirror, goes off a couple other mirrors through this lens, and then into our guide camera. So we have actually a brand new guide camera there as well that was just installed earlier this year. But she's put in a little system here, this little red camera, and it's got some optics in front of it that detects the turbulence. And so we have a little flip mirror that just flips a mirror in and set it so light, instead of going to the guide camera, goes to the wavefront sensor camera. So over on the right-hand image, here's our guide camera, that the big yellow circle that's obscured is our guide camera field of view. And this black blob is the flip mirror sending the light to the wavefront sensor. Anyway, she's just started testing this instrument a couple nights ago to see if it works. So I don't have final result. I was hoping maybe I'd have an image from the new wavefront sensor camera to show in the talk today, but it's too new. I did not manage to get one in time. But knowing what the turbulence is the first step to correcting the turbulence and making your telescope work better and give you better images. So that's coming up sometime in the next year. We will have that fully functional. Other things with wavefront sensors detecting the turbulence is this thing called a pyramid wavefront sensor. Now, I'm not going to go into the details of how wavefront sensors work. That's a whole hour-long talk on its own and fairly technical. But pyramid wavefront sensor is a relatively new technology that was developed in the 1990s, and we don't use it here at Lick Observatory. But essentially, to measure the turbulence, you split the light up from the telescope into, typically with a pyramid wavefront sensor, 4 spots. The innovation here is that we're splitting the light up from the telescope into 3 spots. And that means that each spot gets more light. So you get higher signal to noise in each spot for measuring the turbulence. And that also means that maybe you could do natural guide star corrections with fainter stars because you're dividing the light up a little less than in the standard wavefront sensor. Unfortunately, I don't truly understand how pyramid wavefront sensors work, other than that there's an actual glass pyramid prism in there that you focus the light of the telescope on the peak of the pyramid and then use a little motor to sort of move it around to what's called modulate it. And that helps you measure the turbulence. As I said, all very complicated, but this is work being done by Dominic Sanchez at UC Santa Cruz. And so he's been developing this. I have some software I need to install on the computer to help them get it working. this is what the actual hardware looks like. I know, very obscure. You probably have no idea what you're looking at. It just looks like a bunch of metal boxes and wires, but the pyramid wavefront sensor is hidden here behind sort of this yellow box with computer cards and cables that run it. And then there's a little wheel that moves the spot around on the peak of the pyramid, and then 3 spots actually, from the wavefront sensor itself. Turbulence. As I said, all very obscure how it works, but trust me, this is very promising for allowing us to do better correction on fainter stars and get those really high resolution, high contrast images that everyone so loves out of their telescopes. Another new instrument that's just been installed is called astrophotonic spectrograph. And this also goes in our adaptive optics system, because what they're doing is they're taking light that's already been corrected. So you have nice, very, very sharp images of your star and feeding that light into a fiber optic. And that fiber optic then can is a special thing called the photonics lantern. It will divide the light up and send it to a spectrograph. And so you can take spectra with very high resolution and with a very compact thing. Most spectrographs are huge things. And the advantage of using photonics is sort of like a shoebox size instrument. So it'd be really easy to put on sort of any telescope. And we hope be cheaper to manufacture. But this is all work being done by Kevin Bundy and Matt DiMartino at UC Santa Cruz. So the gizmo you're looking at, the blue box is our infrared camera, the Sharks infrared camera that's part of our adaptive optics system. And the light comes in the front. So we're actually not sending light to the camera, but going into this prism and then being sent off to these, the top leg of optics and the bottom leg of optics. You can see a fiber optic here that's taking the data and sending it off to these photonic shoebox sized instrument. Photonics lantern, I truly don't understand how they work. Mode fiber and single mode optical fiber combination. I won't be able to answer questions if you have this, but some of the data that actually looks like is at the top left image, we're actually looking at diadem, which is a 0.6 arcsecond binary. So the adaptive optics system is running. You can see the 2 stars separated by 0.6 arcseconds, so that yes, we can see stars with this instrument. On the top right, we were looking at Alpha Hercules A. Alpha Herc is a binary star, pretty bright. But you can see the light is going down into the fiber optics. So we know that we're getting light into our system. We can also see at the bottom right, Alpha Herc B, we can, separate it by a prism and send it into a different fiber optic if we wanted to. So we're making progress. Again, this is all brand new technology. We've just installed, just starting to test. So we're hoping that we'll do that. And I think the last thing I'll talk about gets us back to the search for extrasolar planets. Another key research thing. I try not to take too much time here. But one of the things with adaptive optics that I mentioned before is that it uses a mirror that changes its shape, maybe 1,000 or 1,500 times a second to correct for the turbulence. The Automatic Planet Finder telescope, we're working on putting an adaptive secondary mirror in. So usually the adaptive mirror is like after the primary, down in, in the instrument, not the secondary mirror. But it's much more efficient if your secondary mirror is the adaptive element, because every time you put an extra mirror into a optical system, you lose some light. And so by having the secondary be adaptive, you can, not lose any more light than you're already using. And why would you need this for a robotic telescope that detects planets around other stars? Usually adaptive optics is used for a system to do high contrast, high spatial resolution imaging. And when you're using a spectrograph, you're usually just spreading the light out. You're really not concerned so much with that high resolution. But it turns out that there aren't enough telescopes in the world. We already actually knew this. There are more astronomers doing research than there are telescopes available for them. But the telescopes like the Kepler Space Telescope and the TESS telescope that are discovering exoplanets in huge numbers. But if you want to measure the masses of those planets, you really need to take a spectra and do the radial velocity technique that our automatic planet finder telescope uses. And it turns out there's just not enough telescopes that have the right equipment to do this. And so when you take a spectrum, you have to get all the light through a tiny little slit, a tiny little aperture. And you can see in this animation that the light goes all over the place, but the slit is only ½ arc-second wide. So we actually lose a lot of the light. If we use adaptive optics, shrink that core down, make it more stable. It's like having another, a telescope that's 2 or 3 times bigger. And so that you can get more light down that slit, take shorter exposures with the same signal to noise, and then move on to the next star. So that this makes our existing really efficient APF telescope more like having 2 or 3 of those telescopes, so that we get a lot more data, can measure the masses of a lot more planets around other stars. And so lots of really exciting things going there. And this is all work being done by graduate student Rachel Bowens-Rubin at Santa Cruz. And yes, I'm focusing very much on Santa Cruz because that's where a lot of our technical shops and the laboratory for adaptive optics are. And then I'll mention one final new project, which is planned for later this year. And this is putting a full adaptive optics system on the nickel 1-meter telescope. And it will use a laser, but its plan is to use not a yellow laser like the Shane telescope does, but an ultraviolet laser. And so our eyes won't be able to see it, but the goal is to not just correct in the near infrared, which is what the Shane telescope does. It turns out that adaptive optics works more easily at longer wavelength light, the near infrared, the light longer than redder than our eyes can see. But we want to push the technology so that we can do observations and do corrections in the optical, look at green and blue light and have good adaptive optics correction. So by having a powerful UV laser to create a fake star, we can measure the wavefront there and then do corrections in the optical. So this is something that's it's being built right now. And Mark Ammons for the Lawrence Livermore Laboratory is the head of this. In fact, he was just here at Lick Observatory today, making measurements on the telescope so that he can make sure he builds an instrument that's not too heavy. Right now, his instrument's a little too heavy for the telescope with his current design. So lots of things to consider. But again, we'll be able to do this fantastic imaging with the nickel telescope in addition to doing it with the Shane telescope. So, in summary, I'd like to say that, Lick Observatory was at the forefront of technology in 1888 when it was originally constructed with the largest telescope of its kind in the world. And we continue to use new technologies and develop new things to make our telescopes operate better. And of course, all of these technologies, if they're successful, will migrate to the larger telescopes like the Keck telescopes in the world. And finally, I'd like to say that Lick Observatory, not only do we do research, we are open to the public. You can get more information at lickobservatory.org. We have a visitor center that you can come visit. In April, our tickets will go on sale to our public viewing events and concert series. We also have a friends organization, and we have, if you're here in person, of course, you can shop at our gift shop, but we also have an online gift shop. So with that, thank you very much, and I'll take any questions.
Thank you so much, Dr. Gates. Really exciting, especially all the new equipment. Hopefully some of that, makes up for all the for being closed for so long and all the hardship that the observatory went through in those last couple of years. but
Yep.
very exciting. I know we have several of our own docents here are super jealous of all the, the equipment. Does anybody have a question? You can either put it in the chat or if you'd like to unmute yourself, that's probably fine as well. I think it was Christopher Wright, I believe. Go ahead and unmute yourself.
Thank you. Can you hear me?
Yes.
Wonderful. You mentioned the search for newer supernovae and whatnot.
Yeah.
Is the telescopes that you're using attached to some of the world's neutrino detectors as a way of early warning or early detecting supernovae before they reach the visible spectrum?
So I'm not 100% sure, but I'd be surprised if they weren't. Alex Filipenko, who's the head of our supernova group at UC Berkeley and runs the Kate telescope, already has connections for interrupting regular observations for gamma ray bursts and such things. So I would be very surprised if he wasn't involved in getting notifications from the neutrino detectors about new supernovae.
Awesome. Thank you.
Don, go ahead and unmute yourself.
Hi, Dr. Case. About 20 years ago, you're giving us a tour of the Shane telescope, and I asked you, what was it like to look through the 120-inch telescope? And you're saying you had to go up into the prime focus cage to collimate the mirror when it came back in. Do you still get to do that?
So no, the prime focus cage, I was the last person to use it in 1998 when I started working at Lick Observatory. So I'm the last person to have the good fortune to look through the telescope with an eyepiece at the prime focus. However, I think I may be the only person in the world who has looked through the Shane telescope with an eyepiece at both at the prime focus, the Coudet focus, and the Cassegrain focus. So we built a mount to put our Cassegrain focus many years ago. So yeah.
This is spectacular still.
Oh yes, it never ceases to be amazing.
Thank you.
Stephen Moore had a good question. What is the status of light pollution from the urban area affecting Lick's equipment? Is it worsening, and are there mediating measures?
So yeah, that's might lead to a very long answer. So yeah, light pollution is definitely a problem. It is definitely getting worse, both because the Bay Area is just getting more populous in general. But there's the advent of these digital billboards, and they have switched from the very lovely low pressure sodium lights in San Jose that were installed starting in the 80s to help Lick Observatory preserve our dark skies. And at the time, it was a win-win because they were the most energy efficient lights available at the time for street lights, as well as just emitting light at the one color yellow that we could filter out more effectively. But now LED lights are much more energy efficient. And of course, people like the white light better than those yellow lights. So that's broadband interference. So what Lick Observatory is doing was we're actually changed our focus. We tend to do larger surveys of brighter targets, say looking for exoplanets, or we've moved to doing more science in the near infrared because the light pollution in San Jose is all optical light, so it doesn't affect the near infrared. And of course, we focus very much on our education and technology development activities, which are not as affected by the light pollution. So we're adapting. I mean, we do talk to the San Jose City Council and zoning commissions and stuff to try and make sure they implement more light pollution mitigating measures. It's an uphill battle.
I can imagine. Christopher also asked, how far away are we from being able to see or detect weather patterns on exoplanets, do you think?
That's a good question. I mean, at this point, we've just now gotten to the technology where actually we can detect atmospheres and what their atmospheric compositions of some of these exoplanets are. I think we're still a ways away from being able to really know what's happening weather-wise and how that's, or even if there are different, northern parts of, or the polar regions are different characteristics than equatorial regions. I think we're a ways away from that. But the James Webb Telescope is really pumping out amazing data, and so it might be closer than I realize.
Good point. Another question regarding measuring the afterglow of colliding neutron stars. How long does the afterglow last after a typical collision?
Oh, that's a good question. I can't remember. I know it's I think it's actually I shouldn't say anything because I just don't remember. So I'm sorry, I'll have to look that up and get back to you.
No worries, no worries. Christopher, just a comment. If I were a few decades younger, I would love to study to be an astroclimatologist.
Yeah, well, there's lots of stuff that's that's coming. I mean, it's we're working on astrobiology, astroclimatology. Who knows what else is coming?
It's exciting. Anybody have any other questions? I just had maybe a quick question that perhaps we can close up with, unless somebody else has another question. But how did you get into adaptive optics? What was the path for that?
When I was an undergraduate, I did an internship at the National Radio Astronomy Observatory and became very interested in high resolution imaging. And at that time, I was using radio interferometers, the VLA and VLBA. And then when I returned to New Mexico for graduate school, was the same year they had a meeting between astronomers and the military about high resolution and adaptive optics. The astronomy was sort of catching up with the military capabilities for adaptive optics. Now, the military was not looking at astronomical objects. They're mostly looking at imaging satellites and space surveillance sort of systems. But there was that collaboration, and I discovered that, hey, I could do high resolution astronomy in the near infrared and optical and really, expand my knowledge base. And it's just really interesting. And so I spent some time as a graduate student working at the Air Force Phillips Laboratory on their adaptive optics systems. And then Lick Observatory, it was still brand new technology in the 90s. I mean, it's just, it just wasn't being used in astronomy for taking data. It was just being developed. And Lick Observatory had a test system that was built by Lawrence Livermore Labs, and they needed someone that knew adaptive optics. And I was one of a very few number of people that knew anything about that technology at the time. And so I was fortunate to be hired by Lick Observatory to help take their research and development system and make it into something that astronomers could actually use.
Oh, sorry, I think you cut out right at the end, but
No.
Oh, there you are. Well, that must have been super exciting to be on that cutting edge of technology. That's amazing.
Yeah, and of course that continues today. I hope I didn't, completely confuse people with the sheer number of projects I talked about, but I hope you got a sense of how exciting it is.
Absolutely. No, absolutely. Thank you so much. I don't think there's any more questions. So thank you for all of you I know we're a little bit after 8 for sticking with us, and a huge thank you to you, Dr. Gates, and hopefully you'll join us again sometime for a future presentation. Maybe once all this new technology you talked about is up and running and you can share data about that, we would love to hear about it.
Yep. Thank you.
Thank you. Thank you very much. Have a good night, everybody. Bye-bye.